Okay, so this talk is a little bit different, I think, from Ian's. I didn't consult the Cable survey, and I didn't check out the SDFC website either. I took a slightly more personal view, and so I'm going to talk about things that are perhaps a little bit closer to what I do, what the people in the gravity group are up to. And I'm taking the view, which I believe could be true, that the current decade is going to be the decade for transient astronomy, where things that don't go boom and don't go on for a long time, but sort of happens for a shorter kind of time, but still long. And the next decade after this will be the era of, well, one might call the dark ages, where we're going to be exploring things that Ian talked about, the dark matter, the dark energy, black holes, and so on in more detail. So that's where I'm going with this. At the heart of all this would be Einstein's theory of general relativity, partly because that's what I know something about, perhaps. At least blag about it for about half an hour. So that should be okay. So, general relativity is not a new idea, of course. It's been around for near 100 years now. But as you'll find out when you go through your physics career, it is one of the two main building blocks of what one might call modern physics, even though this modern physics is all of it 100 years old. So it's maybe old physics, but it's still what we use. So the important thing here, I think, is that you hear a lot about general relativity, etc. What's important to say is about the principle that it's a theory, it's incredibly well tested. It's tested in solar system physics, extragalactic physics, it's tested in things like the GPS system every day. It's tested in double neutron star systems, I'll come to neutron stars in a while, with extreme precision down to fractions of a percent. And it's tested in our ideas of the evolution of the universe. So this is big tests. Some of them are maybe not particularly accurate, if you like. But general relativity is not some sort of fancy thing that mathematicians think of. This is very near to what reality probably is like. Now, having said that, it's certainly true that still 100 years after the conception of this theory, it's perceived as difficult. So you can ask, there's this famous quote from Eddington about saying that there's only 2 people or 3 people, whatever it was, that understands relativity, and he was including himself in that. If we were to ask people in the street today who understands general relativity, they would say, well, that's that Hawking chap. There's just one. So why is it that general relativity is perceived as difficult? Well, the answer is very simple. It involves objects called tensors. In order to calculate with tensors, in principle, you need to know something about geometry. So you need to understand a little bit more about the language of mathematics at the beyond A level. So that is difficult to the everyday man in the street. But my way of thinking about this is to say that, okay, look, Chinese is difficult. Yet there's 1 billion people on the planet that speak Chinese without any apparent trouble. Relativity is a little bit the same. You need to learn a bit more, like grammar and so on, maybe how to write proper Chinese characters and how to speak it, and then you can be fluent. Theoretical physics is like that. It's like learning a language. So when people say, oh, I don't understand math, you go to the hairdresser, where do you go? Maybe at the pub, or somebody to buy someone a pint, you say, well, that math stuff is too hard for me. Well, that might be because this person stopped doing any kind of mathematics or any theory kind of stuff at age 15, so at age 46, whatever it might be, maybe, there's a gap compared to someone like myself that carried on for some reason and never really got a real job. Okay, so the essence of general relativity is that space and time are combined into a 4-dimensional entity called space-time. It's not just a dead sort of thing, it's a live thing that reacts to the presence of matter. And so in the words of John Wheeler, the famous statement that matter tells space how to move, and space tells matter how to burn. Oh, it took the other way. You can read it. I can't see anything from it. And so the idea is this: you've got some blob of matter. It will affect the geometry of space and time, and then as it moves, that changes, and the back reacts on the motion, and that gives you gravity. So we've got two bodies, how they move around each other is an entirely geometric problem. And so that idea is a little bit complicated. The idea of how you measure things in general relativity, familiar notions like things happening at the same time and so on are all gone out the window, become observer dependent. It's a little bit messy to take in, but it's a perfectly fine sort of construction that works very well. Now, as astronomy evolves, the kind of ability that astronomers have to look at the universe improves all the time. So the telescopes get better. They can look for weaker and weaker signals. They can look for more, further out in the universe, etc. As this happens, the need for detailed, fully general relativistic models of the kind of things that Ian talked about become larger, become greater. We're not yet at the point where it's compulsory for every practicing astronomer to be an expert in general relativity.
It's getting that way.
It's getting that way. My view is that in the next 10 years, that we're going to get to the point where if you're going to be a proper X-ray astronomer, radio astronomer, etc., you will have to understand general relativity. And so that's a big, big change in how this landscape that we're talking about. So, what about general relativity? Well, it's the world of funky ideas. So this is talk about outstanding, challenging, and so on. So what are these ideas? Well, what comes with general relativity are things that maybe have become part of the mainstream language, but if you look at them in detail, we don't actually understand them very well. So we've got neutron stars. Basically, what happens when big stars die, they form either neutron stars or black holes. And these objects are completely different. I'm going to talk about both of them in a little bit more detail, but not much. To ideas that belong uniquely to general relativity or relativistic gravity, if you like. So the idea of gravitational waves, ripples in this space-time curvature that describe how gravity changes locally, so how that information propagates out from the local region. Ideas like cosmic censorship, that if there are singular points in the universe, in this space-time fabric, they have to be closed by an event horizon, so they have to be inside the black hole. Whether that's true or not, that's still not completely proven, but this is a concept that comes with general relativity. And then all the way up to the origin and evolution of our universe. From the Big Bang, that essentially says in general relativity there is a point where things begin and the universe expands from that point, it's a singularity at the beginning, to the notion of dark energy, as Ian said, which could simply be a pesky constant entering the equation. Big mistake or not, but it appears that there is something like that out there. So I'm going to talk about neutron stars and some of the problems, basically try to give you a flavour for what this kind of thing is. What is it we're looking at when we work on these things? Talk about black holes and I'll talk about gravitational waves. I'm not going to talk much about the other things because I don't want to rush over just lots and lots of things. I'm going to give you a flavour of some particular things. There is a part of this that I'm not going to talk about, which is where gravity meets particle physics. I've chosen not to do that for the same reasons as Ian. I expect Nick Evans to do that when he gives his talk later. Okay. So let me start with neutron stars. So this is my own favourite area of research at the moment. Neutron stars are fantastic. Basically what happens is a massive star dies, but it doesn't form a black hole. It's not quite heavy enough to form a black hole. So it collapses to form a very, very compact star, so compact that the atoms are pushed together to the point where the electron shells give, and you push all the way down to the nuclei themselves. So essentially a neutron star are nuclei bound on top of each other onto a ball that's about 10 kilometers in radius. 10 kilometers is not very big, and this thing weighs more than our sun, about 1.5 times as much as our sun. Now, the funny thing that happens is that when you push matter together to that point, you reach densities at the center which are up to maybe 5 to 10 times as high as in the atomic nucleus. When you do that, you enter what one might call physics at the point where nothing is funny anymore, or maybe physics at the point where everything is funny, because it's the kind of physics that we can't probe in laboratories. So the best laboratory we have for testing extremely dense matter, so what quarks do and so on, is Large Hadron Collider. You know. So Large Hadron Collider is an experiment that essentially tests what matter does at high temperatures and relatively low densities. A neutron star is extremely cold in comparison and much, much more dense. So you can think of this as a parameter space where the Large Hadron Collider probes the region up here and neutron stars probe physics over there. So this is why nuclear physicists, particle physicists are extremely interested in trying to come up with models for what matter does when you compress it to these extreme energies. So that's why there's a part of physics that likes neutron stars. There's another aspect side of neutron stars, which is the astronomy. It's basically saying that we know now that there are something like, we've seen more than 2,000 neutron stars in the shape of radio pulsars, X-ray pulsars, gamma ray pulsars, and so on. Some of them are in double systems, like the famous binary pulsar that I'll maybe mention later. Some of them are not. From population models, we expect that there might be as many as 2 billion neutron stars in the galaxy. We only see a couple of thousand, so for some reason, most of them are not seen. That's kind of interesting to figure out. Is it our observatories that are not good enough or whatever? But these guys are an incredibly rich phenomenology. You can probably argue that there are no two of them that are behaving exactly the same way, and many of them are quite unpredictable, which makes it a very interesting problem to ask. Can we put together a model that puts in all the physics we need to understand all the stuff that we see? So here's the challenge, and this is what I try to pretend that I work on. You take all the physics that you've learned, sort of up here, a bit of electromagnetism, fluid dynamics, nuclear physics, particle physics, superfluidity, so cold condensed matter physics, a bit of thermodynamics, gravity, and maybe QCD, sometimes QED if you like. Bung it all together and you calculate. Out should come a model that predicts the astronomy that we observe. Now this is a very, very hard problem. It's a hard problem because there are very, very few people that have got the theoretical muscle to take on the problem with all these ingredients. In fact, there's probably nobody on the planet that can do all of this, and therefore people work on various bits. So, as I see it, one of the big, big challenges in theoretical astrophysics is to come up, as Ian alluded to, with models that actually make sense vis-a-vis the observations, but are firmly grounded in the physics. And we are nowhere near able to do this. There are many reasons. So here's a very typical reality. We see many of these neutron stars in terms of radio pulsars. They're essentially lighthouses that spin and have a little beam that go around once every time it goes around. You see that beam go pop in the detector once every revolution. We've seen these objects for 40 years, a bit more, 45 years. We still don't know what the mechanism is that leads to this radio emission. There's no model that actually works on the market. 45 years, complete failure. My daughter told me last night, epic fail, Daddy. That was not about that though, that was something completely different. Okay, so there's a lot of problems where so the key point here is all the way from when neutron stars are born in the supernova explosion to when they perhaps die in double star neutron star systems where the stars collide and maybe lead to a gamma ray powerful gamma ray burst. There is a lot of different physics, different technology in terms of calculations and modeling. All the way from pen and paper up to the largest supercomputer simulations that are done currently in science. So if you want to study the collapse of a star in a supernova explosion, that's a massive computational challenge. It has to put in all of this physics into the numerics. Very, very hard. Or you can do the kind of stuff that I do, fiddle about with pen and paper a little bit and then come up with some idea and pretend that it's good. So it's a big, big range, but all these things ultimately should come together and sort of make sense. In contrast, black holes are very, very simple. In order to describe a black hole in general relativity, you really only need two parameters. How much it weighs, mass, and how fast it rotates, the spin. Theoretically, you might also need something that describes electric charge, but in reality, that's likely to be completely irrelevant because if you place a black hole with electric charge somewhere in the universe, it's going to attract particles of the opposite charge and neutralize. So therefore, you only need two parameters. You need a rotating Kerr black hole. So if you go back to the 1960s, so basically my lifetime, in the 1960s, end of the 1960s, we started having real evidence that there were black holes in the universe. At that point, the research papers about black holes were almost exclusively written by sort of freaks on the gravity side. Right? Today, this is almost completely changed, and black hole research papers are very much written by people in astronomy. I probably don't know very much general relativity. Black holes have become part of mainstream language. So everybody knows what a black hole is, right? You've watched Horizon and all these things, probably seen Stephen Hawking talk about these things. You know what a black hole is. Not so. Sorry. The problem is, we've accepted this change, and we're pretending that we're seeing black holes all the time in observations. I'm not a skeptic, I'm fully with the program, right? But we're not sure, and this is another big, big issue that Ian sort of touched upon, we're not sure that the black holes that we see are the black holes of Einstein's theory. In order to establish that that is the case, you need to look much, much closer to the black hole than we're able to. So the best that we have, here's the best evidence, I think, really, that we have, but there are certainly big black holes out there. There is a set of, I really like this movie, so I'm going to show it. There's a set of data from the Galactic Center Group at UCLA using the Keck telescope. And what they're doing is they're tracing out, simply they're just pointing the telescope at the Galactic Center and seeing what the stars in that region do. They watch them trace out their orbits. So why is this such an amazing piece of science? Well, it's an amazing piece of science because you can see one of these objects, it's called S0-2 for some really good reason, but executes a complete elliptic orbit. Right? Now you probably all know Kepler's laws. So this elliptic orbit says, well, there should be something in the middle, essentially at the galactic center, which is a very faint yellow star you probably can't see very well there. And you can work out, simply based on how long it took this guy to go around, what the mass has to be. So there's a number you will get, it'll be something like, 3 million times the solar mass, alright? But you can't see it. So what is it? Well, our opinion is that it is a black hole. Because we're now going to reach the point where this is not the crazy idea, but the most conservative idea that we can come up with. anything you want to put in the middle that's dark and that compact is more exotic than a black hole. So that's a huge evolution over a 40-year or so time span. But where we're going, where we should be going, is to establish that this is indeed an object that behaves exactly like the theory says. In general relativity, there is no doubt. If general relativity is exactly the correct theory, you don't have any wriggle room. The object has to be exactly that of this current solution to Einstein's equations. If it's not that, then the theory is wrong, or might have to be adjusted a little bit. So that's the precision test. We're not there yet. You can, in principle, hope to do this, but so probe the near region, such as say these orbits, which take about 10 years to complete, are something like 10,000 radii away from the center. So if this object is a black hole with a certain radius, these are probe the regions of 10,000 radii away. That's hardly near in any sort of sensible definition of the word near. But the accretion flows that Ian talked about, so when a black hole sort of feeds on gas and matter floating around it, probe the region much closer to it, and ideally, with higher precision X-ray astronomy, we should be able to make sense out of what goes on in that region. What it takes is really good observational capacity and much, much better theory understanding of how matter flows in strong gravity. And I think that, together with the origin of the powerful jet outflows that we see from many active galaxies and smaller black holes as well, is one of the big, big questions. To get the modeling and the observations to go hand in hand for those problems, it's a massive problem for the next sort of 10 years or so. People have worked on this for a long time, but there's a long way to go. Connected with this, another probe of this is what happens when two black hole systems merge. When two black holes merge, or a black hole merges with some star, with a star, or a big or small star. The reason why this is important is a problem that, again, Ian talked about, the problem of how do you build structures in the galaxy, and if there is a black hole the size of 1,000,000 times our sun, whereas the biggest stars we had early in the universe was maybe 1,000 times that of the sun, how could we build this beast of 1,000,000? There are black holes predicted to be 1,000,000,000 times as massive as the sun. Where did they come from? They seem to have formed quite early in the universe. How did that happen? That's another big, big problem. The evolution of these massive black holes and the close connection of question, why is it the case that there seems to be a massive black hole at the center of every galaxy, more or less? Why is that? Are they central to this formation or not? That's sort of bits of the story that are still missing. Another unique aspect of general relativity is the idea of gravitational radiation. It's essentially saying that in relativity, nothing can travel faster than the speed of light. So if gravity changes, say as two stars go around each other, the information how gravity changes has to propagate out slower than the speed of light or at the speed of light. The theory predicts that it does so by emitting essentially waves of gravity. And so this is one of the remaining things in the theory that have not been tested directly. So we have this system called the binary pulsar and the double neutron star system as well, which tests the theory by saying that if you have this emission of gravitational waves, a binary orbit should shrink at a certain rate, and that's been tested to better than 0.1% over 30 years or so for a particular system. So we sort of know that the theory is correct, but we haven't built a detector that has seen these guys directly. And that's what we want to do. I think we're working on quite a lot in the group over in the gravity group. And so why spend such an effort in doing this? Well, the reason is not just because we want to prove that Einstein was right and it's all fine and dandy in relativity land. We want to use gravitational waves to probe the physics that we can't see with X-ray telescopes or normal optical telescopes and so, or radio for that matter. And so there are problems that are very, very important to this entire story of how the universe works, which involve things that are basically dark. Typical one would be, what happens when a star collapses? So we can't see that because there's too much gunk going on in the sort of explosion part. But when a star collapses to form a black hole, that's something you can only really hope to see in the sense in neutrinos or in gravitational waves. Because you would be looking at gravity itself, this is the best channel to try to ask what is the detailed nature of these black holes. They are made from gravity, so the best way to look at them is in the gravity channel. Neutron stars emit gravitational waves potentially in many different ways, so we can address issues like this state of matter thing that I talked about. There will be, should be, some level again as Ian talked about, gravity wave imprints in things like the cosmic microwave background that will tell us perhaps something about dark matter, dark energy and so on, and tell us what happened in the very early universe. So I think perhaps the most fundamental observation that is possible in astronomy would be a gravitational wave signal from the Big Bang itself. Because it will be emitted something like 10 to the minus 46 seconds after the Big Bang. You cannot conceive of going back any earlier than that. Now that's a very difficult observation most people think we will never make, but if you're looking for challenges, and that Nobel Prize that Ian promised, then that's it. So here's a picture of what the gravitational wave spectrum looks like. It's sort of farming around a little bit with the idea of looking at the optical. The key point here is that you're looking at different timescales. So physics have different timescales. For milliseconds, the typical dynamics of an object with enormous densities like a neutron star, maybe going around another neutron star or an exploding star, which happens on a millisecond timescale, all the way down to the seconds, the hours, to typical hours, days, very common timescales in astronomy, all the way down to the age of the universe. So it's really, really long. So gravitational waves come into this picture because gravity is central to a lot of things in the universe. And basically you have to then try to look at these things in different ways. We've got telescopes like the LIGO telescope in the United States, which a member of the gravity group here is working with, which is a 4-kilometer size, with two 4-kilometer sized vacuum tubes where you point lasers down and try to measure distance very, very accurately. We've got a telescope called LISA that's now called something else because it fell foul of the budget cuts when we had to bail out the banks. So that might not happen in my lifetime. It will still be a supreme black hole telescope. It's always been top ranked for the science, but unfortunately the budget for science has been dramatically cut, and so that's now looking quite shaky. The radio pulsar guys are looking at things that happen on timescales of years for these kinds of systems, and they're coming up very, very fast. And if you were to start making bets on who's going to succeed first, they have a real shot at it, whereas 5 years ago they probably didn't, but now they do. And then finally, there's some very big thing in cosmology trying to figure out what the gravitational wave imprint is on the cosmic microwave background. So basically, I think this diagram tells you the whole story. Gravitational physics enters into pretty much anything you can think of when you think about the universe, and you can just take your pick. Whatever sounds exciting, there are difficult problems there to pick. So I'm getting near the end. I just think it's worth considering the following. So we're used to looking at different wave bands in the electromagnetic spectrum. So here's an example of galaxy M81, different pictures are stolen. So all the way from X-ray up to radio. It obviously looks different depending on how you look at it. But it's still all electromagnetic systems. Apart from that, all we know about the universe comes from neutrinos. We haven't really detected that many neutrinos. saw a few from supernova 1987A, and there's some solar neutrinos here and there, but it's not really a big thing that you can just go out and detect billions of neutrinos every day and you really learn a lot about physics from them. It's still very, very challenging. Right? So, my view is this. The gravitational wave window provides a completely different piece of information. So it complements what we know, and there's no other way that we can get this information. And that's why it's so important. Is it going to happen? It will happen. In fact, I would stake a very small bet, my fortune, that I will never make, that we will have a detection of gravitational waves after 2016, say, when the next generation of detectors come back online, because they're being upgraded at the moment. And then, if this goes well, people like me are no longer going to be theorists making crazy predictions. I'm going to be an observer that does real observations. And then there's a good final thought, sort of final thought. I've got one little addendum that I've added for you, which is this. In the 1930s, before radio astronomy, the universe was seen as this cool, calm and collected place where things happen very, very slowly. Then radio came on stream, X-rays. In the 1960s, we now know that the universe is full of explosions and things that go whiz bang pop. So when you open up a new observation channel, you find that things aren't quite as you expected. And that's a big lesson for you if you're looking for where is science going. Well, you've had us to talk about this, but frankly, we have no idea. It's going to be the unexpected that's going to be the next big thing. And we can't talk about that because you don't know what it is. So I'm going to leave you with a more personal reflection, because I'm now, to my horror, no longer a young scientist. I've become a senior academic, so I need to think about my legacy. You know? So I've got this thing sent to me from a friend. You can read it. I think so it's got to do with how people write their big book. As you know, every scientist, we get letters all the time from people saying, why don't you write this big book? They don't call it the big book, but they say things. Ian, why don't you write this big book on this important book on X-ray astronomy and black holes, right? And then we say, oh yes, that would be nice, but I'm a little bit too busy. So I've thought quite hard about this, right? And I've started several times. So I'm going to admit another epic fail. Okay? And the reason why it's so difficult for me is I work on neutron stars, right? So here's a version of what this book would look like. Right, it's got some of the words, right? I need to know probably about this portion: neutron star, physics, problems, superfluid, understanding gravitational wave dynamics, right? So I've worked on it. I've really made an effort. And I've clearly failed. So I decided to take a completely different slope, and especially for you, today, I did something completely different, okay? And this is the book that I wrote. It's available on Amazon. It should be free tomorrow. Thank you.